This conference will now be recorded.
Very good evening, students. Today we will be completing this 4th September 2022 Shift 2 paper, and by that we will actually complete the whole JEE Main, like all the papers in this session September. Okay, so in this PYQ discussion series we will pick up some other year, or maybe we'll take the January session also for 2020 in the next subsequent classes. So let us start our today's business. So here we have got a problem related to Houston Bridge. You can see this is not exactly Houston Bridge, but the shape of the circuit looks like a Houston Bridge. So four resistances, 40, 60 ohm, 90 ohm and 110 ohm make the arms of a quadrilateral ABCD. Quadrilateral, okay? Quadrilateral ABCD. Across AC is a battery. Across AC there is a battery of EMF 40 volt. The internal resistance negligible, okay? Internal resistance are negligible, like internal resistance of the battery is negligible. The potential difference across BD, what is the potential difference? Okay, what is the potential difference across BD? So that is what we have to find out. Okay, so to solve this problem, this is very easy problem if you know the process how to solve it. First of all, see, you can see there are two arms which are parallel, right? So both the arms actually will drop this 40 voltage itself. Okay, that means if I just stretch out these two things, this is point B, this is point C, this is A. Excuse me. Further, this side you have this point is D, this both are identical, A and C, and here you have further this point C, and this is connected to a battery 40 volt, right? So this is your 40 ohm, this is 60 ohm, and this is 90 ohm, and this is 110 ohm here. Okay, so what is the potential difference between this? That means you have to find out what is BB and what is BD. Look, this BB, see, the voltage across AC, okay, voltage across AC is 40 for both the arm. If I just see this, see these are 100 ohm, this 100 ohm actually will drop this much 40 voltage itself. Here 200 ohm will drop 40 voltage across them. Okay, now how do you find out the voltage of this point B? How do you find out that voltage? Actually, we can find out the voltage drop across 60 for getting the voltage of point B. Okay, if you want to get voltage of point B, then you have to find out the voltage across this 60 ohm. Similarly, voltage at D will be the voltage drop across this 110 ohm. So how to get that voltage? So voltage VB will be then, so the total voltage divided by total current, let us say total current will be, see, across this 40 volt divided by 100. This will be total current, and voltage across 60 I am finding out, so IR. So this will give you 24 volt. Okay. Similarly, 40 by 200 into 110, right? So this will give you 22 volt, right? Then what is this voltage difference between, or potential difference between B and D? 24 minus 22 volt, which is 2 volt. Okay, so here it will be 2. All right. So this is how you have to solve the problem. Now we'll go to the next problem. This problem is very interesting and very important also. Look, this problem says the distance between an object and a screen is 100 centimeter. A lens can produce real image of the object on the screen for two different positions between the screen and the object. Okay. The distance between these two positions is given. Okay. That is 40 centimeter. If the power of the lens is close to n by 100 diopter, then n, see, where n is an integer number, the value of capital N is dash. You have to find out the value of capital N. See, there are two ways to do this problem. If you know the formula, you can directly put it. I'll just explain you what is this formula, like what is the formula related to this problem. See, here the question, let us understand first. See, this is object, this is screen. Okay, this is object, this is screen, and this is a convex lens. So if we change the position of this lens, suppose this is the position 1 and this is position 2. For, okay, so this the distance between these two positions are small d, suppose, and the distance between the object and the screen is capital D. Okay, so we know that for each position, the image, final image is formed on the screen. For if we take this as position, okay, length position, so this will be U, okay, and this, the whole length will be V. In another case, if I take this as U, capital, see this one as U, then this will be V. Okay, so this is the situation, and the distance between these two positions of the lens is small d. So in such case, the focal length has got a formula. So in such case, focal length of the lens will be given by capital D square, that is the distance between the object and the screen, minus small d square, that is the distance between two positions of the lens, divided by 4 into capital D. Now let us put the values. So given here, see, capital D is given as 100 here, and small d is given as 40 here. If we put the values, then we get, see, 100 square minus 40 square divided by 4 into 100 again. So let us see here. If I take 100 common from both, then I'll get 100 minus 16 divided by 4 into 100. See, my answer will be f will be n by 100 by 100. So one thing has come here. So I'm not just striking this 100 out from both like numerator and denominator, because I need the value of the focal length in terms of some value by 100. So this is 84, right? So I have got 100 into 84 divided by 4 into 100 in the denominator. So this is actually in centimeter. Now see, this will be 21. So 2100 divided by 100. Okay, so if I say n by 100, if I just compare with n by 100, then the capital N will be equal to 2100. Okay, so this is one way, and very simplest way. If you correctly remember what is capital D, what is small d, and whether it is this sign is plus or minus, if you can remember properly, then you are done within a minute. Okay, within a minute you will be able to solve this problem. If you don't know, then see, we can actually go for some other process. See, in this case, actually, let me tell you, this, if the length distance, see, if the object distance is u, then the v will be this much. Okay, so now this distance is actually 40, and this distance is actually 100, right? And see, if I say this distance is x, this distance is x. Okay, this distance is x. Let me just take some arbitrary number. If this is 30, you know, this, if this is 30, since the total distance is 100, so the v will be actually, v will be, suppose first set I take u1 as minus 30 object distance, then your v will be 70, right? V will be 70. Again look this one, this much is how much? This is 40, this is 40. So what is the distance between this second position of the lens to the screen? That is going to be actually 30 only, right? Do you get my point? I'm repeating. See, if this u is 30, then since the screen and object distance is fixed, so obviously image distance will be 70, right? This is first image distance. So if the object distance is 30 from this first position of the lens, then image distance from the lens will be obviously 70. Again, I have to take the second position that has got a distance from the first position of the lens to be 40. That means this distance is 30, right? This distance is 30. Okay, with respect to my first position, with respect to my first position, suppose my first position was 30 here, this much is 40, then this position, obviously this position is 30, isn't it? Now if this position is 30, this is the image position for the second position of the lens. So you look, this will be interchanged. Sorry, this is V2. So this is actually interchanged. So this will be 30. I hope you are getting my point. I'll just repeat once again with x. So let me repeat this with x. See, this is 100, this is 40. I have to get two positions for the lens. So first position, say this is x. So what will be this much? This is 40. I know if this position is already fixed, right? If this is some, like this is the first position, then the second position will be 40 centimeter away from the first position. So I know this 40 plus x, this one, okay, right? So this distance I know. Then what will be the image distance from here? This will be 100 minus, say 100 minus x, first image distance, and first object distance is minus x. Okay, you can take this mod also. So in the second case, what is this distance then? See, in second case, so this is actually 40 plus x, this distance. So this is 40 plus x, the total distance is 40 plus x, this one, okay. Then how much is remaining? How much is remaining? Remaining is this much. See, I get 100 minus x minus 40. This much is remaining. That will be the image distance for the second one, okay, v2. Okay, so I hope you have understood this. In the first case I have explained. So in this case we can say, see, once again I'll just make it a little bit simpler. So in first case the object distance is x, okay, then image distance will be 100 minus x, 100 minus x, okay. So within this I have, say, 100 minus x is this much, okay. Again this is actually, so this is 40. From here 40 plus x, see, let me write it, 40 plus x is equal to 100 minus x, right? 100 minus x, is that correct? This is 100 minus x, so that is equal to actually 40 plus x, okay. So generally what we do, if this is x, so the image position will be 100 minus x for the first position, but the image position in the second case, if this is 100 minus x, so then only the image will be formed both the time on the screen, okay. So we get x plus 40 is equal to 100. So that is what I can say, is equal to 100. I'm just, last time I'm saying that if the distance, object distance for the first lens is x, then image distance from the second lens will be x. That is what we have shown you, okay. So finally what we are getting, this is x plus 40, which is actually 100. So 2x is equal to 60. So what is x then? X is equal to 30. So 30, so let me take for this one, this 30, so image distance, if I write 1 by f is equal to 1 by b minus 1 by u. For the first length, if I have taken 30, so this is the image distance. Image distance is how much? So if this is 30, if this is 30, then other part will be v will be actually 70. Okay, this is 70 plus 70, and this is minus 30. Okay, x is actually minus 30. So minus of minus 30 I have got, right? So I get ultimately this, and then this is, and this will be 70 plus 30, which is 100. So f will be, sorry, f will be this much. So capital N, in both cases we are getting 2100. Okay, so this is the answer. Let us go to the next problem. So this problem says orange light of wavelength 6000 10 to the power minus, so this is angstrom. Okay, 10 to the power minus 10 nanometer, sorry, 10 meter illuminates a single slit. This, the maximum possible number of diffraction minima produced on both sides. Both sides of the central maximum. Okay, so you can see this is from single slit diffraction. D sine theta is equal to n lambda. So in this case we have to find out what is maximum possible number of diffraction. That means this n you have to find out. Okay, and for maximum number of n, this theta will be 90 degree. Theta will be 90 degree. Okay, or less or equal to 90 degree, we can say less or equal to 90 degree. That means, you know, this number will be less or equal to d by lambda. Okay, so if we put the values, d is given as 0.6 into 10 to the power minus 4. D is the slit width, that I can write 6 into 10 to the power minus 5 meter, divided by this 6000 into 10 to the power minus 10, which I can further write 6 into 10 to the power minus 5, and here 6 into 10 to the power minus 7. Okay, so if you do the calculation, you will get actually 100. So, you know, this will be less than 100, less or equal to 100. So for maximum maximum number of diffraction minima, we take n minus 1. That means actually 100 minus 1, that is 99, and both side it will be multiplied by 2, because your central diffraction maxima will be like this. Okay, then minima will come. Sorry, let me read all this. So if suppose this is your central maxima, somewhere like this. Okay, then like that it goes on both sides. See the order of this, and the first minima, first second, so first maxima, the order are actually symmetric on both sides. Okay, so that's why both side it will be there. So the total number will be actually, see, the possible number of diffraction minima will be this 2 into n minus 1, that means 2 into 99, which is 198. Okay, we'll go to the next problem. This problem says the speed versus time graph for a particle is shown in the figure. This speed versus time, the distance traveled by the particle during the time interval 0 to 5 second. See, if I see, distance is actually the area under the speed versus time curve. So this is actually 8. See, you have to get actually the area of this part. Okay, so area of this part is the distance. Let us say distance is d, so this is half into base is 5, and then it is height is 8. So this will be, so ut, so it will be actually meter, 20 meter. Okay, in meter this will be 20. This was a very simple problem. Now this problem, the value of current I1 flowing from A to C in the circuit diagram. Okay, in the circuit diagram, the value of current I1 flowing from A to C. See, this is the arm A to C. Okay, here actually we'll be able to apply the concept of Wheatstone bridge. As you see here, you have to find out the current I1. For that, you need to know whether there will be current flowing in any other branch or not. Okay, at least through this branch, whether there will be current or not. If there is no current, then you will be in safe position. Obviously, you can see that this is the voltage across this AC is, so voltage across AC is how much? Across AC is 8 volt, right? Now what is the current? See, you know the resistances in this branch, then it is easy. Directly you can do that. Even say in this way you can see, if I just go for the Wheatstone bridge concept, then you look 2 by 2, so P by Q is equal to R by S. This is equal, so there will be no current through this BD. Okay, this branch there will be zero current. Okay, zero current. So, and see in this figure, I think you need not know even this, whether there is a current through this BD or not, because see this shape showing that there is no connection between this BD branch and AC branch. Okay, if I have a connection like this, then your wire is going like this, so that means actually this is just jumping over it. It is not connected to the other branch, so no need to worry here. You know the voltage drop across the branch, and you know the resistance of the branch. Then what is stopping you to find out the current? So I1 will be total voltage drop 8 volt divided by 4 ohm, sorry, 4 for 8, 4 plus 4, so total you have 8 ohm, right? 8 ohm, so this will be in ampere, so you get 1 ampere. Okay, no need to think too much here. By seeing this figure you need to understand that there is no connection between this BD branch and AC branch. Okay, and see this AC, across AC the same voltage is applied actually, that is 8 volt across this. Like if I go through this way also, you will get the same. Okay, all right, fine. But if somehow they would have asked me what is the current through this, then through this BD branch, then I would have applied Houston-Bridge formula, okay, or law, Houston-Bridge, that principle. So I would think that this is a Houston bridge, then take the ratio of these branches, then probably you will get zero current through this BD branch. Okay, all right, let us go to the next problem. So this problem is also very important problem and also very easy problem, finding out the binding energy. So find the binding energy per nucleon of teen SN50-120. Mass of proton is given 1.00783 atomic unit. Mass of neutron is given like this. The mass of teen is given. Take 1 U is equal to 931 MeV. Then what is the binding energy per nucleon? This is important. Okay. Binding energy per nucleon. Okay. That means what? You find out binding energy EV, divide that value with mass number. Okay. That is binding energy per nucleon. Let me tell you how to find out binding energy. Binding energy actually mass defect. Binding energy delta M into this C square. Okay, delta M into C square. This is the binding energy. Okay, if the mass is in atomic unit, you first find out delta M and then multiply this 931. You will get this in MeV, million electron volt or mega electron volt. Okay, this V will be caps. Okay, so how to find out delta M? Delta M, we know this. Delta M will be, see, Z, sorry, yes, so Z into MP plus number of neutron N into Mn minus the mass of the teen, okay, that is mass of the, like, atomic mass, okay, mass of the teen nucleus, sorry, not atomic, nucleus mass, okay, mass of the nucleus, MSN. So this will give you the mass defect. Okay, if we put each and every value, I have already done the calculation. You can just go and solve it. Like, you can just go and do the multiplication part, addition and subtraction. See here, Z is actually 50. So 50 into MP is given as, see this mass of proton 1.00783. I'll tell you one thing here, you should not approximate anything, otherwise you will not get the correct answer. So you have to take this all 5 digits, okay, because this factor is actually very large. Even if you get very small difference over here, this will make that difference very large. Okay, then number of neutron, see this is 70 and the mass will be multiplied with this 867. Okay, so this multiplication you have to do quickly, since 70 and 50 are there, so these are not going to make lot of hardship, because only one number you have to multiply, and then do the subtraction. This one 119 point, sorry, 902,199. Okay, so this will be in U unit, and this you will find to be 1.097 62. See, I have kept at least 4 digit I have kept. Okay. So this will be actually in atomic mass unit U, and if you want to find out the mass per nucleon, sorry, binding energy per nucleon, then you have to multiply this 1.0962 with 931 divided by 120. So this will give you approximately 8.5 MeV. Okay, this is just a matter of calculation. Okay, just a matter of calculation. You have to do it carefully, otherwise nothing was there in this problem. Okay, and one more point, as I mentioned, this is binding energy per nucleon that you have to remember. See, binding energy per nucleon is not E by Z, it is actually E by A. That is, binding energy divided by mass number is actually called binding energy per nucleon. Okay, so this is all. I think this is how we complete this session, like all the papers of this session, September session. Okay, so next day, I mean in the next session, we'll go for the January session of this, and after so quickly we'll try to solve this January session of this JEE Main 2020. Okay, then we'll go for 21 paper, 22 paper, etc. Okay, so thank you for your patience. Bye for today.
This conference will now be recorded.